Ladies and gentlemen, let's observe the next slide. So here I have some example of the conductor and semiconductor. So the comparison of the Hall effect properties in the conductor and semiconductor. For example, copper strip and gallium arsenide strip. The carrier, both of them are electrons, but the number of electrons difference. Okay, so this means that in conductor there will be 8.48 times 10 to the power 28 more electrons than semiconductor. Semiconductor less. So as a result, the mobility, mobility of electrons in copper are low and in semiconductor are very high. So collision frequently, this means that in semiconductor is low, conductor of copper strip is very high. Also, electrons and hole annihilation when subject to magnetic field, when the presence of magnetic field. So this means it's very frequent and very rare for semiconductor. The VH, carrier drift velocity, VH. So this means that the drift velocity for the conductor is low, but for the semiconductor is high. Drift velocity, this means that the electron move faster. Current flow faster. So Hall effect, so conductor is 0.44 microwatt and the semiconductor will produce greater Hall voltage. And the application in Hall device, conductor none, but semiconductor used in sensor and live wire detector. What is meant by live wire detector? Live wire detector, still remember just now, the introduction. The introduction for the, later, yeah. So for the, at the beginning, the introduction for this diagram, that means that we use the Hall voltage to determine the live wire. So when we let the two and touch the wire, then show the reading. That means what we make sure, actually we make sure the Hall voltage. The 20 ampere show that the Hall voltage. So we use it to make sure the live wire. So next, as a conclusion, we can say that the generation of the significantly large Hall voltage can only occur in a semiconductor. For a conductor, electrons drift velocity is small, where in a semiconductor, electrons drift velocity is higher. This is caused by high mobility of charge carrier, low rate of collision between the charge and the lattice atom, and the n is smaller. Now the application, the Hall effect application, Gauss meter or Tesla meter. So that means that we have a plot. This is the plot. It's used to make sure. So magnify. That means that the structure of the sensor here actually a conductor which apply the electric and magnetic field, and when the current is flow through, produce the Hall voltage. The structure of the bar magnet, if we put a bar magnet here, we notice that there will be for example, there will be show some reading. So these are the structure of the Gauss meter. So how we use it? Okay, so flexible cable connected to the meter, the computer. Okay, so we have the plug and the whole voltage measured by the wire. So here flange will be the GAAS plate strip and also provided with the current flow in the wire. So we magnify. So you see here the conductor flow through by current apply with the magnetic field. Okay, now no magnetic field yet, right? But the whole voltage measure. So solenoid, okay, when put into the solenoid, we can measure the magnetic field. When there is a magnetic field present, so it produces the whole voltage. Because just now, without any magnetic field, right? When we put it near to the magnetic source, the magnetic field, okay, produce the whole effect. The whole voltage measure can determine by using the calculation. We can calculate the magnetic flux density. How strong is the magnetic field? Okay. From the expression of pole voltage, VH equal to BI over NTE. If VH is measured, okay, VH is measured by the whole plot, and I, T, and N are non-value for the semiconductor strip in the plot. Therefore, B can be calculated as B equal to VH over NTE over I. So that means the reading show that actually is a B by using VH over NTE over I. So 1 Tesla is equal to 10,000 Gauss. 1 Gauss is equal to 1 flux line per cm. Or 1 Tesla equal to 10,000 flux line per cm square. Okay, so that means that this we call that is the B is the Tesla. Tesla is a unit for the magnetic flux density in an area of 1 cm square. How much of the electric flux and magnetic field line or magnetic flux? So from here, the whole effect can be used to determine the density and of a charge carrier in a semiconductor. This means that VH is measured and VI, V and I and T are non-value, then N can be calculated by. So this means that we measure how many electrons, number of electrons in the semiconductor by using N equal to BI over VH TE. Okay, so these are the some of the example. They are the example of the plot meter. So now we notice that the whole effect application to determine the drift velocity. As we know that the drift velocity is whole VH is equal to BVD times D. VD is equal to VH over BD. So when we make sure by using the device, we get the VH. Then over the B and D, then we get the drift velocity of the electron. Next, this is the application just now. We use to determine the live wire. So from the V hash equal to Bi over NTE, right? So this means that I can be expressed as V hash NTE over B. This means that we use the magnetic field and also the Hall voltage to determine the current flow in the live cable. That means we no need to cut the cable and connect like the ammeter connect in series. We directly touch the meter. We make sure the whole voltage without spoil the meter, without spoil the wire, without cut the cable. Cut off the cable. We also can determine the current flow in the cable. So this means that this use the concept of the whole voltage VH equal to I over NTE. So I equal to VH NTE over B. Okay, so that means everything we just need to make sure the B, the device make sure the B, then by using the calculation show us the current flow in the cable. Next. So Hall effect application for the N-type and P-type semiconductor. Semiconductor A and semiconductor B. So is there any difference? Now we notice that current flow. So that means that if positive and negative terminal apply, positive and here negative. So what happened is it current flow in this direction. So current will move in this positive charge, okay, positive to negative, positive move in this direction, and negative will move in this direction. Sorry, current. Okay, so later, yeah. Electron is moved in opposite direction. Impossible, negative. Okay, so let me find out the should be like this negative. Okay. N-type, P-type. Okay, this will be the P-type semiconductor. Okay, so why? Because that, okay, this positive charge is more. If same thing, okay, this will be if positive side, negative side. That means that current flow. That means that the positive charge now will be negative charge. Negative charge in opposite direction. Okay, majority is the negative charge. Majority is negative charge, so it will be N-type semiconductor. Okay, if positive charge carrier inside, so that means it becomes the P-type semiconductor. Negative charge carrier is a majority charge carrier, so it will be N-type semiconductor. So as a summary, as a conclusion, the Hall effect is applied in numerous applications. They are used as Hall effect sensor to measure magnetic field or magnetic flux density in a device called a Hall plot. To determine the average drift velocity of charge carrier VD in semiconductor research is to use to determine charge carrier density N in a conductor and semiconductor. How many charge carrier? And next, used to measure remotely current in live wire using a device called a clamp meter. And to determine the polarity of charge carrier, negative or positive, in a conductor and semiconductor. And it's used to the pole, determine the pole of a magnet. Okay, so that's all for today's lesson. Later, I will post as usual, I will post the question for today's lesson on our Telegram group. So, student, please solve the question and before you check the answer. So here will be the answer. Sorry, here will be the question. Question number 1. Question number 2. Question number 3. Question number 4. Question number 5. And next page, question number 6. And finally, question number 7. Okay, so ladies and gentlemen, that's all for today's. Thank you very much and solve the question before check the answer. See you tomorrow. OK， so 各位同学，那么我们今天我们就到这边 ，OK。